So I'm going to go over the daily two, all right, but I'm actually going to use a webcam. So it's going to kind of serve as a document camera. I want to see what you're seeing. Okay, so I'm going to change to my document camera here. Like this. Okay, now, so daily two, number 34, number one. Okay, number one has talking about Bill, who can exert a force of 300 newtons on a box, and his friend Gil, who can exert a force of 250 newtons on same box. And part number one says, what is the maximum amount of force that can be exerted on the box? Well, let's say this is the box. Okay. Now, if Bill exerts a force to the right of 300 newtons, and Gil exerts a force in the same direction of 250 newtons, that will produce a maximum force with them working together of 550 newtons. Okay, and so let's take this 250 vector, place it tail to tip at the end of the 300 newton vector, and then the resultant of those two will be 550 newtons, and that's the maximum that can be exerted on that box. Okay, and that's the answer to number one. Now the answer to number two, what is the minimum that can be exerted on the box? All right, the minimum force. Well, that's going to happen when Bill, say, exerts a force to the right, and Gil opposes that. Okay, opposes that 250 newtons to the left. All right, and that's going to result, trying to write that a little darker, that's going to result in an overall force. If I picked up this 250 newton vector, added it tail to tip like that, the end is going to end up right there or something, or the resultant is going to be their difference, or 50 newtons to the right, or in Bill's direction. Okay, and so that's going to be the minimum amount of force. Note that it can never be zero. Okay, because these two forces, even when they're in complete opposition, the net force will still be, the resultant force will still be 50 newtons. Okay, so the maximum that can be exerted is when they're working together, 550 newtons. The minimum is 50 newtons, and it can never be zero. All right. Okay, now consider the angle between these two force vectors. The angle between Bill's vector and Gil's vector here, that little angle over there, is 0 degrees. Okay? Now, what about in this case? In this case, they're in complete opposition, and the angle between these two vectors is 180 degrees. Okay? All right, well now, what happens if they exert at some different angle between 0 and 180 degrees? For example, what happens if, here's the box, if Bill exerts a 300 Newton force like that, and Gil exerts a 250 Newton force, say, in this direction, okay, at some angle x in between. All right, what will be the resultant of these two forces? Well, let's take Gil's vector, add it tail to tip with Bill's vector. It's going to end up somewhere around up there. Or doing this another way, okay, let's use the vector parallelogram method, where we draw parallels, okay, and then draw the resultant from across the diagonal. So the resultant will be something like this, okay? All right, and this will have some value between 550 and 50. What it is exactly, we don't know without doing further work, okay? But never mind about that right now. So it is this. Now, let's increase this angle x. Okay, right now it's some acute angle somewhere between 0 and 90. All right, so now let's actually make it 90. So now down here, okay, I'm going to have Bill's vector. I'm trying to draw them the same length. There's Bill's vector of 300 newtons. Okay, 300 newtons. This pencil shows up the best. Although this webcam is of limited resolution. Let me try getting a little closer. And then Gill's vector, let's just make it at a right angle. Right up like this. And so this is going to be 250 newtons. Okay. Now, we could, once again, add them tail to tip. Okay, it's going to end up here somewhere. Or vector parallelogram method. And we're going to end up with a force vector. And the resultant vector is right here. Now, since the original force vectors are at right angles, we could actually determine the magnitude of R with the Pythagorean theorem. I'm not going to do that because that's not my point here, but we could. Okay. So note, look what happened to the resultant as we increase that angle. All right, we're going to do this one more time. But now, so there's Bill's vector, 300 newtons. And now Gill's vector is going to go kind of off like this, in this direction. So there will be an obtuse, oh, you can't see that, sorry. So now there's an obtuse angle between the two vectors. Okay, what will be the resultant? What will be the resultant of these two vectors? Okay, well, using the same old, you could once again add them tail to tip, and it's going to end up here somewhere, or using the vector parallelogram method, parallel, the resultant is going to be here. Okay. Now, let's notice the trend here. If the angle, going back to the original, I'm going to zoom out a little bit. If the angle was 0 degrees between the two force vectors, we had the maximum value that it can be, 550. Okay. As the angle increased from 0 to some larger and larger and larger value, larger and larger and larger value, look what happened to the resultant. The resultant got smaller. Okay, so as the angle between these two force vectors increases, their resultant, the magnitude of their resultant, decreases. And it decreases to a minimum value of 50 when they're in complete opposition. Okay, so this is the trend. As the angle between these two force vectors increases, their magnitude decreases. Okay? All right? Okay, and in this particular case, it can have a maximum value of 250. Check that. I'm sorry, 550. It has a minimum value of 50, and it can have any value between those two, depending on the angle between the vectors. Okay, that's the point. That's the point I wanted to get across. Okay, questions, comments on that? Friction we are not going to consider here. Okay, we're not going to consider friction. That's a complicating factor that we will ignore for now. Okay, let's just focusing on these two. All right. Okay. Are there any other questions about this stuff? All right. All right, I'm going to set that aside then. Okay. I actually want to do a little review of some stuff that we did in the early part of this unit. Oh, in the way of announcements, let me just switch cameras for a minute. All right, so I was kind of, we're bumping up against the end of the semester here, and I have a test in pre-calc going, and I didn't want to have 2 tests on the same day again. So what I'm going to do is, let's see, get rid of that. I'm not going to have, originally I was thinking about having a test this Friday in physics, but I'm not going to do that. Okay, I'm going to skip the test, and I'll put some stuff on this on the final exam. All right, so there will be no test in physics this Friday. There's one in pre-calc students, but I'm going to skip the test in physics. Now that's good news for some of you. That's probably maybe bad news for others because it's a lesser chance to raise your grade. I'm sorry about that, but I just decided that, and you probably have some tests going on in other teachers' classes also. So I'm going to skip the test in here, and I'll just put a little bit more of this stuff on the final exam. Okay? And do we need to write all this in our notes? Pretty much, kids, if I write it down, you should write it down. Unless I say, I'll never test you on this. You don't have to write this down. I will tell you if you don't need to write this down. If I don't say that, then you should probably write it down. Okay? Just to have it. Okay? And what I just went over is testable stuff. You know, it could be on the exam. All right. Having said all that, are there any questions about what I just went over? Okay. Then what I want to do is I want to sharpen the pencils. And then I want to do a little review stuff. Okay, so I'm going to get my camera going again, my kind of webcam type thing. And I just want to do a little bit of like review of what we've done so far. First part of this unit, we took two vectors and we combined them to form a resultant. Let's do that again, just for fun. Very quick. And I'm going to call this boat on a river. So this is going to be my boat on a river problem. Okay. Let's say we have a river, and I'm just going to have the river going like this. Okay. I have a boat at the north bank of this river. There's my boat. Oh, by the way, I want a reference compass. 0, 90, 180, 270. And let's say the boat is if there were if it weren't a river, but instead a lake, if the water wasn't moving, then the boat would go straight across the river, okay, at 8 meters per second, say. So it's going south at 180 at a speed of 8 meters per second. Okay. Now, let's say there is a current. Let's say there's a current going to the west at 3 meters per second. Okay. Let's say there's a current going to the west. All right. Now, what would the boat do? Okay. Well, let's say my little binder clip is the boat. If you were in a helicopter hovering over this river, watching as the boat crosses the river, it's not going to go straight across because the current is going to take it. The boat instead will take this kind of path as it's getting pushed by the engines and getting pushed by the current. And so the current vector could be added to the engines vector, the boat vector, and the resultant then will be in this direction. Okay. And what we want to find is the magnitude and direction of this resultant. Well, since it's forming a right triangle, we can find the magnitude by Pythagorean theorem, right? So a squared plus b squared equals c squared. So a squared plus 3 squared is equal to the magnitude of r squared. That's 64 plus 9, that's 73, is the magnitude of r squared. Okay, so that means that the magnitude of r is the square root of 73. Calculators, what is the square root of 73? Calculators, what is the square root of 73? Gabby says 8.5. Is that 8.5? Is that confirmed? 8.5? 8.5. Okay, thank you. So 8.5 meters per second. Okay, that's our magnitude. All right. Now, what we also need to find is the direction. And we're going to take the angle at the starting point, which is that one right there. Call it x. And note that I know the opposite and the hypotenuse. Opposite and hypotenuse, I should probably have a little visual here. So opposite and hypotenuse are related by the sine function. Okay, so the sine of my angle x is equal to opposite over hypotenuse, and that's 3/8. All right. And if you divide 3 by 8, what you get is 0.375. 0.375. So my angle then will be the inverse sine of 0.375. Calculators, what is the inverse sine of 0.375? What is the inverse sine of 0.375 to the nearest degree? Calculators? I got a 22. Is that confirmed? $22. Okay, 22. All right, degrees. And then referencing it to my compass, which is kind of like right around like here. So that 22 degrees is right in there. Okay, I have to start at 180 and increase it by 22. So the bearing, starting at 180, increasing by 22, and that's equal to 202. So then my resultant, I would report my resultant then as 8.5 meters per second at 202 degrees. Okay, and that's our answer. Okay. All right, so that's taking two vectors and combining them into a single one. That's a little review of what we did in the first part of this unit. All right, questions about that? Okay, then in the second part of this unit, what we did was we took one vector and we broke them up into components. Okay, and I had you guys work on numbers 3 and 4 on the finding the components of vectors. I forgot exactly how I worded it. Practice sheet from before break, and I asked you to do numbers 3 and 4. And what I'm going to do now is I'm going to share the screen. First of all, I'm going to get this camera, and then I'm going to share the screen. And I want to go over the answers to those. So dig those out, numbers 3 and 4 on the breaking vectors into components practice problems. And I want to go over numbers 3 and 4. I asked you to do numbers 3 and 4. Okay. And oops, I don't think I did that correctly. Hold on just a moment. Did I actually share the screen? I don't believe I did. Forgot about that part. All right. So, okay, that's better. That's better. Okay. So we have a plane flying at a speed of 500 kilometers per hour at a bearing of 240 degrees. We wanted to find the westward component of the plane's velocity. All right, now, so here is the my little reference compass, and there's my vector, 500 kilometers per hour at 240 degrees. Now I'm going to draw the components in like this. So I have a westward component and a southward component. Okay, westward component and a southward component. And there's a 30-degree angle between the westward component and the bearing angle. 270 minus 240 equals 30. So that little angle in there is 30 degrees. Okay, now the westward component is the adjacent side to the angle, adjacent and hypotenuse are related by the cosine function. So the cosine of 30 is equal to the westward component divided by 525. Now, I'm going to solve this by multiplying both sides by 525. And my calculator gave me an answer of 455 kilometers per hour. Okay. All right. Using SOHCAHTOA. Now, let's say instead you decided to break up the vectors like this. Okay. Gee, am I going to get the same? I did it the blue vector way instead of the red vector way. Boy, am I going to get wrong answers? Well, let's find out. Now I'm going to use this angle right up here, and that's 180 and 240, and that differs by 60. Okay, differs by 60. And note that V sub W is the opposite side to that angle, and opposite and hypotenuse are related by the sine function. So sine of 60 is equal to that, multiplying each side by 525 yields an answer of the very same, 455 kilometers per hour. So it doesn't matter how you break up this, the original vector, doesn't matter how you break it up, as I have drawn in red or as I have drawn in blue. Doesn't matter. As long as you pick as long as you get your angle correct, okay, then you will get the correct answer. Okay. However, there is something that I have to warn you about. All right. Let's say you wanted to just use the original 240 degrees. You know, why can't this should give me a right answer, right? Well, I want you to pick up your calculators and crank that one out. 525 times the cosine of 240. 525 times the cosine of 240. What do you get when you do that? You should, if it was the right way to do it, you should get 455, but you don't. Instead, you get negative 250. Now, why is that? Well, for that, I don't know who to blame, but I can tell you why it happens. It's because the navigation system that we use and the system that we use in math class are different. For these sines and cosines, what they take in math class is the positive x-axis is 0 degrees and the positive y-axis is 90. In other words, the 0 is the x-axis and it increases in a counterclockwise direction. For the navigation system on Earth, it is different. The 0 is the positive y-axis and it increases in a clockwise direction. So not only from math class to the navigation system, not only are the zeros in different places, but it increases in opposite directions. Okay, and for that reason, this is going to give you a wrong answer. Okay, 240 degrees according to the navigation system is not 240 degrees according to math class. Okay, and because of that, you're going to get incorrect answers if you just plug in 240 for the cosine. I see it every year. Some kids just put the bearing angle in for their sines and cosines. And I'm telling you, you get incorrect answers. And why? Because navigation, our navigation system, and the system used in math class are different. Now, the way to adjust to it is to always have angles between 0 and 90 degrees. Because that means all of our sines and cosines will be positive. Okay? That's the way to adjust. So you have to use these reference angles. You can't use the original 240. You have to use angles between 0 and 90. Okay? Otherwise, you're going to run into this issue over here. It's going to give you incorrect answers. Okay? So please be aware of that. I want to try to catch that mistake before it ever happens. You have to use angles between 0 and 90 degrees. Okay. Any questions on number 3? All right. And number 4, we have a rope tied to a box held at an angle of 60 degrees. There's an 85 Newton force exerted on the box by the rope. We want to determine the vertical component of the force. So here's my sketch. And I'm going to sketch in my components. So I have force horizontal and force vertical, right? And the angle between the horizontal and my rope vector is 60 degrees. All right. I want the vertical component, and the vertical component is the opposite side. Opposite and hypotenuse are related by the sine function. Okay. So the sine of 60 is equal to opposite over hypotenuse, f sub v over 85. All right. Multiply both sides by 85. And my calculator yields an answer of, to the nearest Newton, 74 newtons. 74 newtons. Okay. All right. Okay. Now, that's part A. Part B, does the box stay on the floor or is it pulled off the floor by the force? And to find out, we need to compare the weight with F sub B because weight is pulling down and F sub V is pulling up. Which one wins? Well, to find out, we need to find the weight of the 6 kilogram box. That's easy enough to do. We just take weight is equal to mg. All right. And then, let's see, to the nearest Newton, that turns out to be 59 newtons. So now we can answer the question. Does the box stay on the floor or is it pulled off the floor by the force? Well, let's see. The weight pulling down is 59. The force pulling up is 74. That 74 Newton force is greater. And so since F sub B is greater than the weight, then the box is pulled off the floor. All right. All right. So this, the second part of the unit, what we did was we took a single vector, be it velocity vector or a force vector, and we break it up into components, perpendicular components. In this case, horizontal and vertical. All right. Any questions about number 4? No? All right. Well, I'm going to stop sharing then and get back to this screen. And let's see, did that. All right. Now, next, I want to talk about what we've been doing in the last part of this. I have to actually get out of my PowerPoint. And so what I want to do is I want to go over what we've been doing in the last part of this unit, and that's talking about equilibrium and the force component vectors. Okay, so as an example of this, and I'm going to change to my webcam now / document channel. All right, and one thing we did, we talked about signs, signs hanging off of buildings. So let's say that you get a business and you open up a store and you want to hang a sign from the store. Okay, and it's a decorative sign with a decorative chain. You have to hold it away from the building. Okay, so here's your sign. Joe's, we'll call it that. All right. Now let's say this sign weighs 850 newtons. Okay, you have to hold it up by a chain, and here's the chain. Okay, and so there's a tension in the chain. All right. Now let's say that the max tension that it can be, the strength of the chain, or something we call tensile strength, is 2,000 newtons. If it's more than 2,000 newtons, then the chain will break. Okay. Now let's say you have this beautiful chain that you want to use for your sign support. It has a maximum strength of 2,000 newtons. There's going to be a limitation as to what this angle can be. There's going to be a limit to a lower limit as to what that angle could be before you exceed the strength of the chain and it's going to snap. It's not going to be able to hold up this sign. Okay, well, I want to find out what that angle is. So let's say you want to, there's not a lot of roof clearance, or you want to get the sign away from the building as much as you can. So you need this angle to be small. What is the smallest that it can be? Well, we can find out by considering force vectors. Okay, now let's just ignore everything except for this little vector triangle and just pull it out of there. Like this. Now, there's going to be a tension on the chain that's going up like that. The chain is going to have to pull up and to the left. All right. Now our angle is x. Now, this tension vector can be broken up into two components. One that's pushing into the building. I'll call that tension horizontal. And then one that has to pull up. And the resultant of those two vectors, okay, will give me the original tension vector. So I'm going to break this tension vector up into horizontal and vertical components. All right. Now, in order for this sign to hold up, or in order for it to be in equilibrium, the net forces on the sign have to be zero. Okay, and what that means is that the weight that's pulling down, there's a weight pulling down. That's the weight vector pulling down. That has to be exactly matched by the vertical part of this tension vector. The vertical component must match the weight vector for equilibrium to occur. So for equilibrium, the tension vector must be the same as the weight. Okay. Oh, by the way, there's another condition. The building has to push back with the same amount of force that this horizontal component pushes on it. That's usually not a problem because buildings are made of brick or something like that. We don't usually have to consider that, but we do have to consider the vertical one. For equilibrium, the tension vector must match the weight. So what that means is this tension, if the tension vector is 2,000 newtons, the max tension, we want to figure out the breaking point. This must be 850. Actually, this has to be 850 regardless of the angle. Doesn't matter what the angle is. This vertical component has to match the 850 Newton weight, or that sign will not stay up. Okay? What I want to find here is this limiting angle x. Well, we can use SOHCAHTOA to do this, okay? Because opposite is 850, hypotenuse is 200, okay? Opposite and hypotenuse are related by the sine function, okay? Sine is equal to opposite over hypotenuse. Sine of my angle x is equal to opposite over hypotenuse. Writing this out, I get the sine of x is equal to 850 over the hypotenuse of 2,000. Calculators. What's 850 divided by 2,000? What's 850 divided by 2,000? Calculators? Calculators? 0.425. Thank you. 0.425. All right, then my angle will be the inverse sine of that. 0.425. Calculators. What is that angle? To the nearest degree. 25? Says Ronan. Is that confirmed? 25. So this angle is 25 degrees. Okay, and that's actually a minimum angle. If you try to have a smaller angle while trying to hold up this 850 Newton sine, that's going to increase this tension to a value greater than 2,000, and that chain is going to snap. Okay, so this is a lower limit on this angle. Can't have any angle smaller than 25 degrees. And that's pushing it. That's at the edge. Okay, you want to have a safety factor. Okay, so we're breaking up this tension vector. Let's go back to what we were talking about. We're talking about hanging a sign from a building by a chain. All this thing does is it holds it away from the building, that stick or whatever it is. The thing that's holding it up is this chain or rope or whatever it is, call it a chain. The tension in that chain has a couple of components, horizontal and vertical. And it's the vertical one that's kind of important because it has to match that weight. If it doesn't match the weight, okay, then the sign will not stay up. All right. And so we can use that to do a little engineering and determine the angle at which that chain must be to the horizontal. All right. Questions? All right. Okay. Then I want to do one more example today, but I kind of want to do a class lab of this. Okay. So, another piece of paper. I'm going to consider thread. Okay. And I want to find out how strong this thread is. How much force can this thread exert before it snaps? Okay. And to do that, we're going to do a little class lab. I got a little setup that I have to do. So it's going to involve this thread and this 1 kilogram mass. Okay. 1,000 grams here. It says 1,000 over there. And so what I'm going to do is I'm going to have this thread hold up this mass until it won't anymore. All right, and I'm going to show you. But in order to do that, I have to take my webcam off, put it on the table in front of me. Okay, and I'm actually, for reasons that will become apparent later, I have to have a white shirt on. And I don't have a white shirt that's plain except for an exercise shirt that I'm going to go off camera and put on. You'll need this as a background. You'll see why in a moment. Okay, so I just got my little exercise shirt down here. And we're going to need this as a background because what I'm going to do is have this mass break. Okay, and I'm going to have a protractor. I'm going to have a protractor behind. And so I have to, give me a few minutes while I set this up. A lot easier to do this when we're in the same place, but this will have to do. All right, so I have a little protractor here. I'm going to lower it down a little bit. All right, and what I'm going to do is I'm going to pick up the mass with some thread. Okay. Now, this is a 1 kilogram mass, so it weighs 9.8 newtons, right? 9.8 newtons. Let me zoom out just a little bit. Now, if I hold it like this, straight up and down, okay, straight up and down, there's 2 threads that are holding this up. Each thread takes half of the 9.8, or 4.9 newtons, okay? But so the tension in each string is going to be 4.9. However, if instead of having it straight up like that, let me get this protractor out of the way just for a moment so you can see. If instead I have the string at an angle like this. Now I'm going to zoom in a little bit because it's hard for you to see the string. If the string is at an angle, the tension in the string is going to grow. And you can feel that yourself as I pull my hands apart to change the angle that the string makes with the horizontal, okay, I can feel the tension in the string increase. I had to pull. The tension in the string is going to increase to the point where the thread snaps. Okay. Well, what I want us to measure is the angle with the horizontal, that the thread makes, okay, right at the point that it snaps. Okay. So that's our task. Our task is to find the angle with the horizontal that the thread makes when the thread snaps. Okay, to do that, we're going to use a protractor. Okay, now, this is kind of a tough thing to measure even when you're here. It's tougher to measure when you're there and I'm here, but it'll be crude, but I'll get my point across. Okay. Okay, now, so I have to try to hold it so that the point of contact is right at the vertex of the protractor. I'm actually going to do this behind it. Let's see. Because I think you can see the thread through the protractor, and it's easier for me to hold it to the vertex. All right, so right at the vertex. I know it's not easy to see this protractor. Let me zoom in a little bit on the protractor, and I'll raise it up a little bit. All right. Okay. So try to get the background. Try to get this as best we can. All right, something like this. No, other way. All right, so now, so I know it's a little blurry, but there's 0, there's 10, there's 20, there's 30, there's 40. Okay. So let's see if we can measure this. It's not going to be super accurate, but I'll get my point across. Okay, so trying to hold it then. It's just going to fall on the floor. It's going to crash on the floor. That's okay. So let's see if I can get this. Oh, the resolution is so poor. You can kind of see it. At least I can see it on my computer. As it's growing, there it's 30 degrees. No, it isn't. Let me try to zoom it out a little bit. Okay. All right. Okay, so there, the string is, there's 50 degrees, there's 45. 30, 25, at about 25 degrees. It broke, I looked at it, it broke right around there, okay, at 25 degrees, all right? Let's see, where'd it go? I'm gonna do that one more time. Let's see, then one more time. I usually have a couple of trials going on here. So let's see, trying to hold it to the vertex. Oh dear. This is tough. This is tough to do. Okay. It's going to crash to the floor. I don't care about that. And so it's going to be lining up with the vertex. Doesn't look like it from your standpoint, but it's lined up with the vertex. And I'm increasing, and I'm increasing. Watch the thread if you can. Watch the thread. It's going to snap right around. Yeah, right around 25 degrees. Right around there. That's where it was. Okay. Okay. So the thread snapped at 25 degrees. All right, now I got to do another reset. We're going to do a little math here. This is a case where the mass was suspended between 2 points. And I call this kind of like a tightrope, all right? So let me put this webcam in here again. And we're going to draw this situation out. Okay, so let me zoom out a little bit. Get the cord out of the way as best we can. All right, so here's what we had. Try to get this like this. So we had a weight. We had a weight suspended from. We had a weight suspended from at the middle of 2 strings. Okay. Now this had a weight of 9.8 newtons. 9.8 newtons. Now, at the point at which it broke, the string angle with the horizontal was 25 degrees. 25 degrees. Okay. And since it was hung from the middle of the string, this angle was also 25 degrees. That's a simplifying factor that's going to be helpful to us. Now, there's a tension in the string. It's going up. I felt it because it was kind of indenting my finger. And so there's a tension here. This is what I want to find. I want to find what the value of that tension was. That's going to be the strength of the thread. Okay? So now if this tension vector is going to be broken up into components, all right? Horizontal, call that tension horizontal, and up, tension vertical, okay? Now, I'm just going to focus in on just this part. So I'm going to redraw this down here. So there's a tension vector going up like that, maybe not quite that severe, it's only 25-degree angle. Let's draw that. And so that's going to be maybe something like that, okay? And that's going to be T. And my horizontal component here, T sub H, and my vertical component, T sub V, angle 25 degrees. Okay, this is what I want to find. Now, what do I know? Well, right at the instant before it snapped, it was in equilibrium. So it was being held up. That means that I know what this vertical component is. Okay? Now, you might think it would be 9.8 like before, but I have two sides to the string. So there's another vertical component over here, okay, over here. If the sign is hung from the middle of the string, and it did, and it was, then these two will be equal. In other words, each string is going to bear half of the weight. So then now I know that this is 4.9 newtons, half of 9.8. Okay, so it's showing up very well, but maybe get the angle of the camera better. Okay, now look, I have a vector triangle, and I know the opposite. I want to find the hypotenuse, and I know the angle. So once again, opposite and hypotenuse are related by the sine function. So the sine of 25 is equal to the opposite over the hypotenuse, which is opposite is 4.9, hypotenuse is T. Let me just kind of lose the middle part of that. So what I have is that the sine of 25 is equal to 4.9 over T. All right, now from here, you have to be careful because our unknown is in the denominator. You can't just divide by 4.9 to get your answer. That's going to give you an incorrect answer because your unknown is in the denominator. All right, now just to get a number, I'm going to get the sine of 25 in my, let's see, sine of 25 equals 0.423. That's what my calculator says. Hope I hit the right buttons. So 0.423. 0.423 is equal to 4.9 over T. Now, how do I solve this? Well, to get it to, if you have an unknown in the denominator, the easiest thing to do is to cross multiply. Okay, put the 0.423 over 1 and cross multiply. That's the easiest way to get rid of denominators. 0.423 times T equals 1 times 4.9. Right? Then divide each side by 0.423. So T is equal to 4.9 divided by 0.423. Calculators, what is 4.9 divided by 0.423? What is 4.9? What is 4.9 divided by 0.423? 11.58, is that confirmed? 11.58. We don't have quite so many sig figs. Let's call it 11.6. 11.6. And that was the tension in the string as it broke. So that is the strength of the thread, okay? All right. When the string was straight up and down, let me zoom out a little bit. When that thread was straight up and down, the tension was 4.9 each for each thread. But as this angle gets smaller and smaller, that tension gets bigger and bigger to the point where it couldn't hold up the thread anymore. Okay? Or it couldn't hold up the mass anymore and snapped. Okay, so that's kind of tight ropes. That's when masses are hung off the center of strings or ropes or chains or whatever. All right. So this is really a study of equilibrium, and we can use components to do this. All right, now I'm going to switch cameras. By the way, any questions before I do that? Any questions about this? I hope you got that written down. You can use this as an example to do some practice problems. So now I'm going to switch cameras. And then I'm going to actually share the screen, but I want to make sure that I have the right. Yes, I do. Okay, so back to my Zoom. I'm going to share the screen for a moment, and here's where you need to go. Go get into the Physics Schoology page. Open up a new tab. Week of November 30 to December 4th. Okay, and signs and tightropes. Signs and tightropes. Click on that, and what you will find is there are 5 problems that are very similar to the examples that I went over today and the Friday before break. But I want to go through them again today. All right, so these 5 problems are due at the end of tomorrow. I'm going to give you 15 minutes in breakout rooms to get started on them. Okay. All right. And I will help as needed. And then tomorrow, these are going to be, I'm going to give you practice points. You don't have to get them right, but I want to see an attempt. Submit these to Schoology by the end of tomorrow. And then I'll go over the answers to them on Friday. All right. Okay. If you have questions, then simply ask for help and I'll come to your breakout room and be happy to help you. All right. But use the examples that I went over today and the examples that I went over last Friday, the last Friday we met, to do these types of problems. Okay. Any questions before we adjourn to breakout rooms? All right. Then, why can I not find the breakout rooms? There they are. Okay. If you have a question, then let me know. All right. Now let's see. Vanessa, you are with Valeria in room 4. So Vanessa goes to 4. Alia goes to 6. Okay. 6. Okay, and Riley goes to 1.